Hi everyone, good afternoon. Welcome to week 7. I'm sure many of you had a great mid-flex, whatever they call it these days, where you don't have to come to class, but it's still a very busy week. Have 80 people in the lecture here today, just super exciting, I guess, given that an assignment's due on Friday. Everyone certainly seems a bit flat today. So we'll try and take things a bit easy. I have a very exhausting day myself, so maybe we can all relate a little bit. How is everyone? How was your flex week? I've never started a... Is there actually things on the chat? Let me refresh the page. I'm not sure if maybe my YouTube broke and I can't see any chat messages, or maybe you're all just quiet. Nope. Oh, no, it was just broken. There we go. I thought you were all just so quiet today. Now I can see them. Excellent. So much to catch up on. What did people do that was interesting? Izzy says flex week was tiring, procrastination, very productive. I spent the week flexing. Happy New Year. The outage killed your internet, and a sewer in your street leaked. Matthew says I really liked the speed-based assignment, internship work, lots and lots and lots of different things. So that's really cool. My flex week was spent catching up on a lot of the work that I neglect because of my UNSW work. So it certainly didn't feel very flexy to me either. But we're back now, and today we're here to talk about probably 2 things. I don't really know how long these topics will take. Week 7 is largely an extension of week 5 in terms of we're just going to keep talking about graphs. Week 8 is going to be a whole new topic on sorting. Week 9 will be just a mishmash of some stuff on hashing. And then we're near the end of the course. We've only really got about 12 hours left of core teaching. And yeah, so we're going to get into the first part today. So this is not a new topic. This is a topic that's been taught in this course forever, I guess. Though it's a new set of lectures that I put together. This topic kind of came up very loosely, I think, in week 2 originally. But I think it's a very complicated topic, and it's something that I don't want to avoid teaching, but I also don't want to go into excessive depth with it because it can just get really confusing. And what we're talking about today with the lecture topic is called P, NP. It's like, what the hell is that? What we're talking about today is that we want a way to be able to generalize different categories of algorithms to understand how feasible they are to solve for a given problem, right? So we've looked at algorithms in this course, like, what did we look at? What did we look at in week 5? I've already forgotten. What graph algorithms? It was Euler paths and Hamiltonian paths, right? We've looked at Euler paths, Hamiltonian paths. We've looked at ways of traversing graphs, breadth first search, depth first search, some bubble sort earlier on. It's been a very data structures heavy course so far, but like we have done a little bit on algorithms. Now, Matthew says, what's wrong with big O? So nothing's wrong with big O. We use big O notation to describe how long an algorithm takes. But the thing is, as we're about to learn, in reality, most algorithms you deal with, and as I said, the aim is to keep this lecture very, very simple because we could take this a lot further. Generally speaking, the algorithms you deal with fall into 2 categories, which are reasonably solvable, even if fast or slow, whatever, and then generally speaking, not that solvable. And the question's been like, well, what do we mean by solve? Solving is essentially getting an answer. So like if you're doing a bubble sort, to solve it is to sort that list of numbers. If you're doing a Hamiltonian path, it's to get the correct path, to get all the correct paths. If you're doing an Euler path, it's to figure out if there's an Euler path or not, right? Now, some of these problems, O1, ON, ON squared, O log n, some of them can be done by computers, and some of them kind of can't. That's the gist we're getting at here, and we're going to go into the detail more of what that means. Firstly, before we chat about this, we want to understand what two really important words solving and verifying. So when it comes to problems that we want to solve in computing, there's the notion of solving it and getting the right answer, and then there's the answer of verifying that you have the right answer. Now, this is something that you probably realize intuitively, but you haven't thought much about it, and I can give you some really simple examples. If you have an unsorted list of numbers and you need to sort it, that's the problem you have to solve. You can solve that problem by doing a bubble sort. We did bubble sort back in week 2. You go through the numbers, you swap them around. That takes some effort. Once it's sorted, though, the next thing you can do is actually check if it's sorted. Or someone can give you a sorted list and say, is this sorted? You can verify whether it's sorted or not. You're not actually trying to sort it. You're not trying to solve the problem. You're just trying to verify if the problem has been solved. So verifying is often easier, but it does take some effort too. In the case of a sorted list, it's really simple, right? If you have an array or a list, you just go through all the elements and you just make sure that the next element is greater or equal to the previous one. That's a lot easier than actually solving the sorting problem, right? Solving the sorting problem, you have to do all these swaps and stuff, but verifying it's quite easy. Some other examples we have here are, forget the easy and hard for a second, but we talked about Euler paths, Hamiltonian paths. I think we touched on traveling salesman as a form of Hamiltonian path, generating spanning trees, sorting a list. There's another one which is a Sudoku, right? Now this is a good example that one of your tutors pointed out to me, because most people have probably tried to solve a Sudoku at one point or another. You probably tried to and again, just in case some of you, Sudoku is that fun little grid thing where you fill in the numbers, and all the rows and columns, and each square has to have 1 to 9 in it only once, right? So really interesting problem. Now, it's really easy to, if someone gives you a complete Sudoku, it's really easy to tell if it's correct, right? It's really easy to tell if it was solved correctly. So if I give you a complete Sudoku like this, you can just go, I'm going to go across each row, make sure that the numbers only appear once. I'm going to go down each column, make sure the numbers only appear once, and then I'm going to go through each square and make sure the numbers only appear once, right? Now, that is verifying the solution. You haven't, solving the problem is actually filling in these squares, right? It's something like this is actually filling it in. Verifying it is checking a solved problem to see if it's correct. Now, in these categories of problems like Sudoku, this and that, in these problems, we try and bucket them, broadly speaking, into 2 categories of difficulty, which I know might sound a bit oversimplified, but those 2 categories of difficulty are easy and hard. What is the difference between those 2 things? Well, we're gonna keep talking about this and looping back to it. But let's try and distinguish easy and hard problems. So most problems you probably come across in this course so far, like sorting, are what you would call easy problems. Which I know sounds kind of strange, right? It's like, okay, well, sure, it didn't sound too easy. Sorting doesn't sound too easy. It doesn't sound that quick. But hard problems, to contrast it to easy problems, are problems that often take a ridiculous amount of time to solve with standard computers that exist. Basically, with the current technology available to humanity, they just take ridiculous amounts of time to solve. And we can talk through the math of this a little bit as well. Most of the time, when we talk about hard problems in computing, they have a big O notation. The most common ones are n factorial, right? Any kind of factorial big O notation, or any kind of power notation where n is the exponent, not the base. So if you think about a lot of the big O's we've seen so far, like on squared, on cubed, O log n, on, whatever, n is the base. N squared, n cubed, n to the power of 4, whatever, n's the base. Then the power is just like a small number, or even a big number, it doesn't really matter. But here, k to the n is the exponent. This is what you would call an exponential problem. It grows exponentially. So as you have 1 input, it's k to the power of 1. If you have 10 inputs, it's k to the power of 10. If you have 1,000 inputs, it's k to the power of 1,000. Now, with these problems, anything that is like these is typically what we call a hard problem. and it requires an extreme amount of time and processing to get the right answer. Generally speaking, we can't solve these problems for any data sets that aren't really small, and we'll talk about some examples of that. Now, this is super random, but I have forgotten to use the toilet before the lecture, so I'm going to go do that now really quick, otherwise I'm going to start getting distracted, so chat in like 60 seconds, sorry. Okay, so when we talk about hard problems, like this gets a little bit technical, so maybe we'll take a pause here and actually go back and talk about like what these exponential things are. So firstly, I'm just going to use Excel for a second here because we like Excel, and there's a bunch of problems that we could, like a bunch of complexities, right? So let's look at like, constant time and n squared and say log n. Maybe I'll put that here. And then we'll jump this up to like n to the power of 4 and like n to the power of 10 or something like this. Okay, so this is like your big O. And then let's say we have our data size sets like 100, 1,000, 10,000, 100,000, 1 million. Like that, except I can't do things correctly. Let me guess the right zeros. Oh, I'm getting it right so far. No, I'm not. Okay, so like super quick, we'll just do that. Now, how long do these things take? Well, we know constant time essentially takes 1, no matter what happens, because it's constant time. We know that log n equals log 100. I can't remember how we do logs properly. Is it by log 2? Is that how you do logs? I've forgotten how to do logs. Let's just do normal log. I don't know. It's probably going to be... That's base 10. Is it? Oh, it must be. That must be how you do it. Yeah. So there's our logs, right? And I'll round those. So these are all relative measurements, right? As in, like, this isn't measured in seconds per se. It's like the number of steps something takes. Now, if we want to actually measure this in seconds, we could divide these by a certain number. And I'm just going to quickly finish these off as well. So this one is going to be that times itself, and then this one is going to be power of that to the power of 4, and then this one is going to be that, or power of that to the power of, what was it, 10? Great, so we have all these different numbers here. And as you can see, these ones are getting so big that Excel doesn't really want to render it. Now this is what you call steps. These are like the number of steps an algorithm takes. Now by now you should be pretty comfortable looking at big O notation and thinking about these. And if I was to kind of take this down further here, and instead of doing steps, let's do seconds. Let's assume that every step is an actual process to do, right? And let's assume that a computer, just for fun, can do 20 million steps per second. 200 million, sorry, I think is a good number. So your processor can do 200 million operations a second. Now this becomes kind of even easier now because I can say, well, if this takes 1 step, then I'm just going to divide it by 200 million, like this. So now that's going to take that many seconds, 0.00005 seconds. And then we can drag this out across here to basically mimic this table over here. Okay, so like this table's the number of steps, this table's the number of seconds. And you can start to see things like anything that's constant time or n is really quick even at scale. Like I don't know how big this is. This is what? 1, 2, 3, 1, 2, 3, 1, 2, 3. This is 10 billion numbers, right? Massive, massive thing. So 10 billion numbers for, n is still 50 seconds. Right, really quick. Like log is like instant. Constant time's like instant. And when we get to n squared, we get to a big number here. I'm not sure if it's going to display it for us. Let's see if we can get Excel to display it for us. Oh, okay. Yep. That's a lot of seconds. Let's actually figure out, like, so how about for the rest of these columns here, rather than doing it in seconds, let's do it in something simple like days. Okay, so we've got, this is how many seconds it takes. So how do we get days? Well, we divide it by 60, then we divide it by 60, then we divide it by 24. Okay, and that tells us how many days it takes to process. Okay, so still like an absolutely massive number. Now, the thing is, you might think these numbers are absolutely massive, but maybe not for n to the power of 10, but maybe I'll just get rid of that example because that might be a bit distracting. But like, these are massive quantities of data to process, billion, 100 billion, whatever, and this is a lot of time. However, there are lots of computers out there that can do things much faster. There are lots of computers out there that have processors that do little sneaky things. There are lots of ways out there to distribute this across thousands of computers, for instance. There's lots and lots of ways to kind of improve these things. And even though this scales pretty aggressively, even though it goes from, 1,000 takes 0.06 of a day to like, 10,000 takes a year or something like this. Is that right? Have I done this correct? Probably. These things are actually not scaling too wildly. Now, all of these different problems, yeah, I don't think they did either. Let me just double check if I've done something wrong here. So let's get these right, because this is very important to demonstrate. 100 squared, 1,000 squared. I mean, these all look fine. I don't really think there's anything wrong with these, is there? Brackets? What do we need brackets for? I don't really see what the advantage of putting brackets in here is, unless I'm really dumb. But I'm pretty sure if you just keep dividing things, it's the same as... Yeah, I don't think there's any difference there. BODMAS. Yeah, I don't think there's any difference there, is there? Unless I just don't understand Excel. I don't think it's... Thanks for the suggestions in the chat. I mean, these numbers don't... Like, these numbers are big, but they don't seem absurd. But the point I'm trying to get at here, and, I should stop getting distracted with the YouTube chat, is that these things scale, but fundamentally, believe it or not, all of these problems still fall into a bucket of problems that we refer to as easy. Okay, and the reason they all refer to as easy is because they are what we call polynomial time problems. They are typically problems that they're either less than n, or they have some kind of log component, or they're n squared, n cubed, n to the power 4, whatever. Now, typically, you're not going to be doing an n to the power 4 algorithm on something that's like 10 billion elements. You just wouldn't do that. But like, say you have one here that's like a million. So doing a million things on this is still an extremely computationally expensive thing. But if you divided that up between enough computers and got enough fast computers, you get that done pretty quick. Say you're doing a big data piece of processing. Say like New South Wales Transport needs to figure out what the route map is or what the ideal timetable is for the year. Okay, it's like, sure, if it takes 3 days to process, it's still 3 days. That's fine. Like 3 days is pretty manageable. Where things get really weird, though, is when you start dealing with exponential problems. So we just talked about easy problems, but let's say we take another set of data down here, except I should really do this one in steps, say. And then let's take the same set of numbers, like here, except now we'll have n factorial, and we'll have, let's just do 2 to the power of n. So two very simple, what we've been referring to as hard problems. Okay. Now, exponentials we get, that's, as Trent says, the classic doubling pond problem. So I don't actually know if, can I do factorial in, yeah, I can. A factorial of, here you go, fact of that number. Whoops, doesn't like that. Fact of that number. Already very large. I might have to start this one a little bit smaller, actually. That might be a smart way to do it. 5, 10, 20, 30, 40, 50. Maybe I'll just go 20, 25, 50, 75, 100. Let's just start with that. This is going to hurt. So here's the problem with these kinds of hard problems, which are generally factorial and exponential. They get really, really big really, really quickly. Now, factorial is a lot worse than 2 to the power of n, but just for fun, let's say 3 to the power of n. Okay, and let's do 3 here. very, very big. And if I go to say like 250, 1,000, Excel's already crapping its pants here, essentially. Excel's literally just saying I'm out. Now, what I might do is I might go back to these problems here, and I might actually put these in a format that is a bit more manageable, like with the scientific numbers, because now you might be able to maybe see a bit clearer how this kind of goes down. So, and I'll just try and make these rows maybe just a tiny bit smaller so everything's visible. Halogen says include n to the n just for fun. Sure, we can include n to the n. See how big this one gets, how quickly. Okay, that one noped out pretty quick as well. Funnily enough, n to the n, like if you actually think about it, n to the n is kind of like n factorial with repeats. If you remember back to permutations, combinations in high school, these are basically combination problems. So when we look at this, what you'll notice is that with these polynomial questions, notice how even though they grow really rapidly, and notice how even though these n to the power of 4 really complex ones get to huge numbers here, they kind of grow somewhat like proportionally. In fact, even though they actually like get bigger much faster, notice how from an exponent sense, their order of magnitude increases are always the same, right? It goes from 8 digits to 12 digits to 16 digits to 20 to 24 to 28. And essentially what this means is even though this problem gets bigger and more complicated, it doesn't, like the rate of increase is somewhat consistent. You're always multiplying it by about the same amount. Where these hard problems get really crazy is that these hard problems completely like blow out of the water really quickly. So we go from 1 to 120 to 3 million to times 10 to the 25. So look at this. For n factorial, when we're dealing with 50 elements, just 50, the real time complexity we're looking at here is greater than the cost of doing an n to the power of 4 algorithm on 10 billion items. Okay? So like absolutely insane. Like literally insane. And that means if you have like a 3 to the power of n problem, right? Like just for 25 numbers, let's put the timings here as well. I'll just put them beside it. So let's put the timings right next to it. So I'll do like timings here. What did I call it? Seconds. So let's do the seconds thing we did before. And in fact, just to keep it simple, let's just make this days outright. So I'm going to say we're going to get this divided by 200 million divided by 60 divided by 60 divided by 24, just to get the number of days something takes. Now, you can see here, again, for like contrast, look at this. If you're dealing with n factorials, maybe I'll make these actual numbers just so you can see them. Oop, that's not good. Maybe I need more decimal places. 5. Okay, so if you're dealing with n factorial, I just want you to pay attention to this. For a data size of 10, right? For data size of 10, these things are, for n factorial, it's really quick, right? It's like fraction, it's quite fast. This is like well less than a day. I don't know what 0.000021 of a day is. I mean, it's approximately 0.018 seconds. Okay, so doing 5 factorial, 10 factorial, 1 factorial, all happens in a fraction of a second. But suddenly, if we go from 10 factorial to 25 factorial, what we're now looking at in terms of seconds is a number I can't, I mean, that's in days. And if I do this by, that's how many days it is. And if I do that by, say, how many years it is, we still get this number. And then if I divide that by how many millennium, like, so between 10 and 25, let's just really emphasize this. 10 factorial, we estimate takes 0.018 seconds to process. 25 factorial takes approximately 2.5 billion years. Okay? Like a phenomenal amount of time. Unless I've screwed up the math, but if I've screwed up the math, the number's still absurd. Like it's as absurd as that. And then very quickly, like the next one here is approximately to the power of 40 times bigger. Like, it's an unfathomably large number. 10 to the power of 80 is the approximation for the number of atoms that exist in the universe. And, there's a billion atoms in a grain of sand or whatever. So these things, so when we talk about, like, what's the slide we had up here? The slide was problems that are hard to solve often take a ridiculous amount of time to solve. So the word ridiculous there is quite literal. Okay, like it's literally it's not feasible. So what a hard problem is, the way I think about a hard problem is generally a problem that's a factorial problem or a to the power of n problem in terms of big O notation, such that it's pretty much impossible to solve problems like it for any number of n that is not really small. Right? It's not like really small, because if we go back now, for instance, and we go look at our week 5 graph algorithms lecture, when we learnt about Hamiltonian paths, this was one of the first algorithms we looked at that had an interesting complexity. The complexity of this algorithm was O of v minus 1. And you probably kind of skipped over this part, but it's like, there's no known simpler algorithm for this task. And what that means is if you want to find a Hamiltonian path, like, oops, sorry, I would have glossed over it. Something like this. Remember, a Hamiltonian path is a path through a graph that touches every vertex once. And what were the applications we had of these again? It was traveling salesman or bus routes. So, if you want to find the most optimal bus route through Sydney that goes to all these bus stops along these edges, we know that the complexity of this is... Sorry, I'm going around all over the place. Oh yeah, v minus 1. So like, let's have a look at this. Well, what's v minus 1? What that means is that if there's 6 bus stops, these are the number of vertices, right? So if there's 6 bus stops, yeah, okay, we can figure out the optimal path through the bus stops through Sydney really quickly, fraction of a second. If there's 11 bus stops, we can still also figure out the optimum way through that. But you know what? If there's 50 bus stops, we need somewhere in the order of magnitude of billions of billions of billions of billions of billions. I think I have to say billions about 5 to 7 times, right? So trillions upon trillions upon trillions upon trillions upon trillions of days it would take to calculate the Hamiltonian path for something of this size. Now, there's a few oversimplifications here. For instance, in the real world, often graphs are a little bit simpler. Like a Sydney bus map is kind of simple enough because often bus routes are like just kind of in a straight line, right? Like, you got buses down Anzac Parade. You have main roads. There's a few things that make these problems not as screwed in reality, but the point is, it's a hard problem. A computer actually can't solve this problem for any number of n that isn't absolutely tiny. Vincent says, is the complexity v minus 1 factorial the time taken to find all Hamiltonian paths, or just the just one? I think it's just one. I don't write this algorithm a lot because most hard algorithms you don't write a ton of, I don't think. Yeah, I'm not sure. I mean, one or many, it's like it's kind of the same thing, because like these kinds of problems anyway, often there's not like a ton of different, so I was just reading, not a ton of different answers. But so I hope I've demonstrated to you, this is quite drawn out, but I hope I've demonstrated to you that these sets of problems that are hard, computers just can't do for any meaningful n. That's the whole simple story. And for easy problems, sure, they can get really time consuming. But still, n to the power of 4 is only like, I mean, how many zeros is this? Like n to the power of 4, let's make this one scientific. Oh, let's make this scientific again so we can kind of compare it a bit easier. N to the power of 4 is still approximately, what, like... You have to remember, like, I'm comparing these two in my head, right? Okay, so doing an n to the power of 4 algorithm on 10 billion numbers is going to be faster to process than... sorry, I meant comparing these two. is going to be faster to process than doing an n factorial on 50 numbers. Like, you're not actually calculating the factorial of 50, right? It's the big O notation's n factorial. But this doesn't mean that it's twice as slow, right? Like, just because it's 26 over 51. Because this number here, right, is 1 with 51 zeros after it. And this number here, right, is like 6 with 26 zeros after it. So it is literally trillions and trillions and trillions of times slower. So even the easy problems are still very digestible in the grand scheme of things. You can for very large amounts of numbers, yeah, it'll be more than 10 to the 15 times faster, exactly. So even with easy problems, for very large numbers, like numbers that we work with as humans, billions, maybe trillions in some crazy case, you can often still digest them. You can use parallel processing, you can use clusters on the cloud, you can go rent 1,000 servers from AWS and run them for a few days. Like, think about these things like the Human Genome Project, right, where they just crunch data, or CERN. It's like a lot of the data they're crunching takes days, months, whatever. It's still a digestible amount of time, right? You can work around it. But you can't work around a problem that if you suddenly put twice the data in, it goes from taking a fraction of a second to trillions of years. This is an interesting problem in computing to do with, it's just maths. And there's lots of problems like this. Shortest path problems are hard problems. A lot of computational fluid dynamics, like if people are interested in mechanical engineering, for instance, we still, like, all the problems associated with computational fluid dynamics, like doing wind tunnel analysis and stuff, like on computers. I know very little about this, and I know some of you would, because some of you would be mech eng or something like this, but it's like these problems, the underlying computational problems to solve how air moves over a cow, these are hard problems, which actually means that, like, all of our computer models to do aerodynamic analysis are actually all massive estimates, because we can't actually fully solve the problem. We have to use estimates. We have to use scaled down models that lose a lot of detail. Like, there's a lot of subtlety here. And this is true for a lot of things. It's true for the traveling salesman problem, trying to figure out optimum ways between things. They're just not super easily solvable problems. And yeah, there's lots of problems like it. Now, back to these points. Hard problems, right? These problems generally can't be solved for large data sets by standard computers. Any algorithm that's hard, like an n factorial or to the power of n exponential, we refer to these as a non-deterministic polynomial time problem. Now, this is a very curious definition, but a normal problem, like an easy problem, like an n squared, a bubble sort, whatever, are what we call a polynomial time problem. So you have polynomial time problems, which are easy, and you have non-deterministic polynomial time problems, which are hard. Now, what a non-deterministic polynomial time problem is that we're saying that you could solve these hard problems, or what we call non-deterministic polynomial time problems. You could solve these if you had a computer, a theoretical computer, that could simulate all possibilities at the same time, or guess the correct answer perfectly right away. Right, so this is where people start talking about quantum computers and what they might be able to do in the future and blah blah blah. It's not what we're talking about today, but the kind of point here is that a normal computer is a deterministic machine. It's like, it follows like a set of steps. Like, if you want to check, like, it's bounded by the laws of physics, right? If you want to check something on a computer, you have to check it and then check another thing. Like, it's all loops and it's all this. So if you need to check v minus 1 factorial different outcomes to see which one's the right one, you have to check all of those kind of in order. Whereas this theoretical non-deterministic machine that can solve non-deterministic polynomial time problems or hard problems instantly is one that could look at every possibility of a Hamiltonian path immediately, like all at the same time, and just guess it. But it doesn't exist. It's a theoretical concept. Or if there was a computer that just knew the answer right away. Like, if every time it did a breadth first search or a depth first search, it just got the exact right answer every time. It's just guessing perfectly. Because guessing is an interesting concept because that's actually what a lot of what we're doing with algorithms is, right? When you're searching a graph or when you're trying to find a Hamiltonian path, you're actually just guessing. You're like, is it this way? No, is it this way? Like, and it's that branching of possibilities that make these problems absurd. Because generally anytime you have branching, you have exponentials. That's kind of how it works. So, like a binary tree is technically 2 to the power of n to traverse. Like we probably didn't talk much about that. Like a binary tree is like a 2, 3, 4 tree or a B tree with like a branching factor of 3. So binary tree is 2. That's actually what this is. Like if you wanna search all the different possibilities through a tree, it actually gets pretty crazy for big numbers of n. So that's what a hard problem is. It's something that can't be solved with computers that we have because the number of guesses or the number of things we have to figure out to calculate it is absurd. It grows at a non-polynomial rate. We refer to the easy problems as polynomial time because they're all polynomials essentially. 2n squared, n to the power of 3, log n's treat it like a polynomial. Yep. Now, let's get back to some terminology. This is the part that is more formal, and I mainly just care about that you've made sense of everything to date. Because that's what matters. That's what matters in your day-to-day lives. So when we're talking about easy and hard problems, generally there's more than this. It gets more complicated, but there's the P's in the wrong spot, I'm sorry. Like the P's funny. There's generally 3 types of problems. Polynomial problems, which are the ones bubble sort, depth first search, Euler paths. And these can be solved in polynomial time, and these can be verified in polynomial time as well. Both of those things. NP problems, or non-deterministic polynomials problems, are ones that can be solved in non-deterministic polynomial time, but can be verified in polynomial time. Now, I could be wrong, but I'm pretty sure a Sudoku is a hard problem to solve, or at least generating. I can't remember. Like it's not saying that you can't generate a Sudoku. It's saying that problem as it scales. Like if I said to you, okay, now make a 16 by 16 Sudoku or a 25 by 25 Sudoku, very quickly that's like a hard algorithm. It just goes out the window. Like if you tried to generate a 64 by 64 Sudoku, I don't actually think it's like feasible. But most NP problems, most hard problems, like Sudoku, like Hamiltonian paths, can still be verified in polynomial time. So most of the things we're talking about here, you can always verify the answer in polynomial time. It's pretty doable. Because finish Sudoku, check it out. A Hamiltonian path, does this touch all the edges? Yes. All the vertices, sorry. Yes, it does. The other type of hard problem that we kind of glossed over was like a combination lock. So people always talk about, like passwords or combination locks. Like if you have a safe at home with 9 digits, what is the time complexity of an algorithm designed to guess every pin code, right? So how let's say an 8-digit pin code. Okay, well that is, there's 10 digits you can press, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And there are 8 digits in the password, in the pin code. So say you're entering an 8-digit pin code. That's big, but it's not like massive. Let me say, it's 10 digits, and let's say this is an 8-digit password, whatever, 12, 16, 20, 24. And we'll say, okay, 10 digits to the power of 8. So that's how many different passwords you can have, or how many different passcodes you can have with a 10-digit passcode. But as this kind of gets bigger, this is technically exponential, I believe. Yeah, so this one is like technically exponential because, as it gets bigger, these get absurd, right? So, and if I try and again generalize how long it takes to guess all of these different passwords, so we divide each of these by 200 million to get the number of seconds very quickly. And then, so if this is like seconds, then this one I'll do days and then years and then whatever. So let's divide this one now by 60 by 60 by 24, and then we'll divide this one by 365. Sorry, clumsy fingers. Yeah, you can see very quickly again, like if you have an 8-digit password, it's like a computer could permutate every possible password in a second. If you have a 12-digit password, it will take them approximately, 0.06 of a day, an hour and a half. If you had a 16-digit password, it's now going to take them 1.5 years, and if you have a 20-digit password, it's now going to take them 15,000 years. So you can actually see the hard aspect of this algorithm, because the n here, the number of digits you have, is exponential. So again, what is a hard algorithm? You can still guess people's passwords. Just because passwords and combination locks are hard problems, it doesn't mean you can't try and solve them. You can try and guess someone's password. And in fact, for small numbers, guessing passwords is really easy. You can guess everyone's password in a second. For large passwords, though, it's not really feasible. And in fact, once you get to a certain size, like this one, even a computer, even all the world's computing power running for years couldn't figure it out, right? So that's kind of why there's the recommendation is to have longer passwords, because longer passwords are safer because it's harder to guess them. I think I'll just preface here that this is a gross oversimplification of password guessing, in the sense that a normal computer would not be able to permutate 200 million passwords a second. And then also a normal password you have, if it's full of all the ASCII characters, would probably have something more like, say, 60 digits. So if I change all these powers from 10 to 60, you can actually see suddenly this goes a bit crazy. Like, an 8-digit password is maybe 10 days. A 12-digit password is now 300,000 years. So, but you get the point. It's exponential. That's what we're demonstrating here. I'm just really driving the point home. So back to NP and NP-complete. So there's this notion of a category of problems called NP-complete problems. And we refer to these problems as ones where they can be solved only in non-deterministic polynomial time. I find this a little bit confusing, because essentially what it's saying is NP problems, some of them, all problems that can be solved with our computers can be solved with these fancy theoretical computers that can do everything, right? So that's why NP is a superset of P. However, NP-complete problems are essentially saying that these problems can be solved only by theoretical supercomputers, right? Only by theoretical supercomputers. That's it. So in reality, you're actually often, in day-to-day conversation, you're often going to be referring to problems as either, is this a polynomial problem or is this an NP-complete problem? So polynomial problems can be solved by our little human computers that can do little things, and NP-complete problems can only be broadly solved by these theoretical machines that don't exist, which means the only way we can solve them is to either develop smart heuristics, which is beyond the scope of this course, go do artificial intelligence, that's quite interesting, or by just doing it for small sets of numbers. And in fact, you've dealt with NP-complete problems all the time, right? Like a ton of combination problems are NP-complete. Has anyone ever tried to figure out like a timetable? Like how do your schools or the universities figure out timetables? How do they how do you combine things in a perfect order given a certain rule? It's like often the only way to do that is actually by a bit of guessing, which gets into the whole heuristic topic. But you've probably had to solve NP-complete problems in your life, but you haven't actually solved them in the sense that you have not created a generalized algorithm that can solve this for all instances. You've just had a good guess at it. And we do this a lot in computing. We often have things that are just good guesses, because we know it's infeasible to actually determine the correct answer or have a method of doing so. So Hamiltonian paths is NP-complete. Yes, I believe so. Again, this whole subject in general is not my domain expertise personally, but I'm pretty sure Hamiltonian paths is an NP-complete problem. It's also technically NP because it can be solved by these theoretical computers. So like all easy and hard problems are NP because they can be solved by these theoretically incredible computers. But it's like, can it be solved by our computers, and can it only be solved by these theoretical computers, which are most problems you deal with. Waleed says, are there problems that can't be verified in polynomial time? Yeah, so this gets more complicated. Great, we're near the end. So this gets more complicated because you can go and read up on this in your own time, but I made a very intentional decision not to make this more complicated because it gets, you can go read up on this. I don't think it's very easy, but this left diagram here is the more accurate representation of how the complexities work, and largely the only thing I've glossed over today, which I have no interest in talking about, is NP hard problems, which are an extension of these unsolvable problems. It's a nuanced part of that. So this bottom circle here with like NP complete P all inside of NP is pretty much what I'm showing you, and I'm not going to be talking about NP hard because we could be here all day. It's very thick reading. We don't expect you to know what NP hard is, and that gets even deeper beyond that. So, and yeah, this gets into the whole problems that can only be verified in NP time. Yeah, so Gorb says, can you re-explain the can be solved in non-deterministic polynomial time? So yes, for polynomial time algorithms, which are what our human computers can do, we can't solve non-deterministic polynomial time problems like n factorial, like 3 to the power of n. And when I say we can't solve them, I mean we can't generally solve them. We don't have a way of generating an algorithm that works for a whole bunch of sizes that can be solved in a reasonable amount of time. Computers just can't do that. So these non-deterministic polynomial time problems can't really be solved by our computers. We can solve it for small numbers, but that's not really solving it. And we can guess sometimes, but we can't actually solve it. And the computers that can don't exist is the in theory. I don't think you can solve every NP problem in polynomial time. I think you can. The point is that you can solve every NP problem in non-deterministic polynomial time, as in all problems inside the blue box can be solved by a computer that doesn't exist. That's perfect. Oh, sorry, I get what you're saying. Yeah, sure. Yeah, and just to summarize this, because let's take a break and wrap this up. So just to summarize, polynomial time algorithms are ones typically in the form of n to the power of x, n square root of n, log n squared, n to the power of 4, breadth first search, binary searches, all these kinds of things. Non-deterministic polynomial time algorithms are then things like Hamilton paths, combination locks, Sudoku generators, and typically things that are either factorial or exponential to n, which is, again, typically combination problems, which is why you start to see this stuff in graphs, because graph problems are largely combinatorics problems. Anyway, that's pretty much all I wanted to share on the PNMP stuff. I just before you open this, let me just double check I actually put the don't open it yet. Don't open it yet. I forgot to put this one in, so we need to put it in. PNP. Let me just move it up. Okay, you can open the link now. So, yes, if you could give some feedback on this lecture, that would be exceptional. Chewy said, so if some galaxy brain came along and made a NP problem P, heaps of problems would be solved. Yeah. it's I think our old head of school used to regularly say that um, he considered computing to be the most important unsolved problem that faces humanity. I think is what he said. I could get that quote wrong. Um, I'll have to chase him up on that. But I'm pretty sure what he was largely referring to was that if humans figure out how to solve NP complete problems, it will have a fundamental change in everything from like, we can do modeling on things we never thought we could, to like we can solve problems we thought were too big, to like we have to rethink how security works. It would be a bigger than the invention of the light bulb or random things like that. So anyway, let's wrap that up. Leave some feedback. Thank you very much. Let's yeah, thank you.